Excellent. All right, everyone. Hey, my name is Daniel Bishop, and we're going to be talking about NG9-1-1 and CAD systems, CAD being computer-aided dispatch, not the drafting software. We're firmly within the world of 911 emergency response today. And as Bill was talking, we have a mouthful for like the title of this talk. And that's because we're talking about considerations on how to balance two data sets, really, which have their own requirements, recommendations. So I wanted to just kind of talk to you about some of the things that I've come across over my time with CloudPoint on how to kind of make these the CAD software requirements with GIS and the NG9-1-1 requirements with GIS kind of balance those two considerations whenever as GIS professionals we're needing to make any data edits or prepare our GIS data to move from E911 to the NG911 standard. So what is NG911? If you're here, you probably have heard of this before. It is a national definition requirement. So it's a national network, which will be able to receive IP inputs from a range of devices. It really opens up the data that dispatchers and emergency response professionals have at their disposal from callers. It's really just kind of a reversal, allowing a network that has concrete location data embedded within the entire process instead of having to kind of backtrack to find where a caller is coming from. It's going to be a direct replacement of the current E911 standard. And it's kind of a system of systems. So we have within each individual state, there will be PSAPs that have territorial kind of authority over that data set, specifically the GIS data set. You can see on the screen a graphic kind of depicting from CISA, the federal government agency, how this GIS lifecycle moving from E911 into NG911 is going to progress. Each state is on its own trajectory. Some are further ahead than others. Right now, where we're kind of situated with this lecture, where it's a bit more useful, is in that procuring the next generation core services to the EZNet build out phase, where this is the phase where we're needing to maintain E911 functionality, because that's what our dispatchers are using, while also building out our next generation GIS data set. So CISA also kind of discusses what the goals of this for GIS, what the goals of NG911 are. And that's really to provide standards and maintenance workflows for GIS data sets. Currently, we can look at E911 as kind of the Wild West. Each individual, PSAP customer CAD software has its own peculiar, requirements or setup. NG911 will kind of solidify a standard nationally for what that GIS data set should be, and how often that data set needs to be updated to make sure that the GIS data that we're using for emergency response is as accurate as possible. And CISA also wants this NG911 to kind of look at a timeline and a path for this transition process from the legacy call routing, which would be E911, into the geospatial routing in G911, and this transitional call routing phase. And that's where we're kind of situated right now for this lecture, specifically looking at that transition, maintaining both E911 and NG. So the first thing we need to discuss is CAD software. A lot of times, from my experience, our GIS professionals are kind of kept as arm's length or only have a vague understanding of how their CAD software within their environment really works. So starting that communication with your CAD system providers is really important, and it's encouraged under several different guidelines. This sentence taken from Guidelines for Developing a State NG9-1-1 Plan. So if you don't have a contact with your local CAD provider, I encourage you to do so and begin that conversation to understand what software requirements, specifically regarding GIS, your particular CAD software requires, because it's going to be as unique as any, it can be unique to any particular instance or location. So what are your CAD software requirements? The things that you really should discuss, and this is the outline for the rest of our talk, is schema. So understanding the field requirements in your attribute data and the format that the CAD software is expecting for those fields. The geographic coordinate system, which your CAD software uses. Geographic coordinate systems are the computerized model of the Earth that we kind of put those points onto within the computer. So CAD software and NG9-1-1, more often than not, are using two different coordinate systems. So we need to make sure that we're transitioning between those two accurately. And then lastly, in this transition phase, database management. The trickiest part, and what's hard for us GIS data nerds, is that we have at the moment two data sets, often independent of one another but related, that we need to maintain. So we're going to look at some best practices and options that you have for maintaining your databases. So taking a kind of a giant step back, for those of you that are unfamiliar with what GIS is or what we're talking about, we're looking at, representing the real world phenomena through digital lines, points, and polygons. So we take the real world, map it onto our computer, and each segment or point relates to a table, and that table contains information about that location. So moving on, the CAD software and NG9-1-1 softwares, when we're looking at these two things, the geometry standards are pretty much aligned. The trick is it's the difference between recommendations and requirements. Often CAD geometry requirements or recommendations align with NG9-1-1 requirements. It's just that NG9-1-1 will have a higher standard to make sure that your data is meeting those requirements. So for instance, your CAD software will want at an intersection, will want your nodes to snap to one another, that there are no overlaps or overshoots, disconnections between those nodes. However, your CAD software will function in general if those things aren't correct. But NG9-1-1 will find that standard will be left a little bit higher, so they'll go and look for, geometry errors. So being mindful of the geometry requirements is important, but for this, because they're aligned, we're not going to spend a lot of time on GIS geometry for this talk. We're going to focus more on schema, and that relates to the attribute table. As GIS managers, we can look at this in three different buckets. First off, we have our local schema, and that's as unique as any individual area. Whatever your GIS system has currently regarding address points or road center lines, that is the local schema. It's individual and it's often unique. Then we have our CAD schema, and that is, like we talked about at the very beginning of this, a reference to what the CAD software is looking for in order to operate correctly. And then we have the NG9-1-1 NENA schema standard. And that is, like I said before, a national standard, a national requirement for the base set of fields. And then each individual state will have an iteration kind of off of that standard, always including everything from NENA, but maybe having a few additional fields, which kind of incorporate the unique addressing styles of individual states. We know that individual states have different ways of addressing. So NENA kind of is the base standard, and then the states will have a little bit more of a complicated schema. So we're looking at attribute data, so attribute tables, and we can see here just kind of a really rough demonstration over our CAD, this middle table row here. We have field representations of CAD software data. And then on the right, we have field representations of the NENA standard. And we can see that there are some there is a relationship between these two. For instance, our from address L left to address left. And then we have over here our from address L and to address L here. So there can be alignment between CAD software fields and NENA fields. However, there can also be, and there almost always is, differences between these two. So those differences is where it gets tricky, and where we need to make sure that we're maintaining both data sets to the requirements that each standard asks for. So our local schema, it can be anything. We can pull this from ownership databases, lead service lines. This could be derived from your assessing or the Office of Assessors, or treasurer's departments. Road center lines could be pavement ratings or vehicle routing information from your highway department. And then we have political boundaries. So local schemas are really derived from the needs of the local GIS department or office. So therefore, this is hyper-focused on the needs of that locality. It's not necessarily looking to a larger standard. Schema requirements, there really are none. Positional requirements, again, there are none, because this is dependent on the needs of the locality. And data consistency, unfortunately, is usually pretty low, unless there is some standard and best practices held within the department itself to keep data as accurate as possible. CAD schemas. So this is, we actually now have a rule or a template that we kind of have to meet. And the schema requirements now are there. However, like I said before, CAD systems themselves can vary from company to company. Positional requirements, they require like road center lines to be snapped at intersections. That's that alignment of geometries between, or geometry recommendations and requirements. And then data consistency. We can have some issues here with data consistency. We have an example of first represented numerically or spelled out. These CAD software, it really depends on the software or the provider that you're using. And this is why I want you to have that conversation with your local provider to understand, possibly gain some clarity if you don't already know what your CAD schema is. Lastly, we have our NENA schema. The schema requirements, again, are nationwide. Positional requirements are higher. They want road center lines snapped at intersections and also address points placed on top of known buildings. So it's just a higher level, a higher standard level from our CAD software. So if you can kind of take heart from this, if you've updated your local GIS data to work with your CAD software, then moving it from the CAD software to the NENA standard is possible. It's really just the same process, but just a bit more stringent on the requirements. Okay, so now let's talk about the coordinate system idea. Oftentimes, CAD software uses a localized planar coordinate system. And by that, I mean, it's a coordinate system that's meant to be used for a small region of a state or the United States. And it's planar, meaning it's two-dimensional. This is because our local coordinate systems that we often use in GIS departments are meant to be A, hyper accurate as possible, and B, very easy to use. And a big thing about a big thing that we want to use coordinate systems for is measurements. So if we have a two-dimensional plane coordinate system, we can easily measure distances on within that coordinate system. NG9-1-1 uses the coordinate system WGS-84, the World Geodetic System, which was created in 1984. That's a global coordinate system, meaning that it encompasses the whole Earth, and it's three-dimensional. NG9-1-1 is kind of transitioning to this global coordinate system so that it can make a unified system nationally. Data that's in WGS-84 for NG9-1-1 in Illinois will then appropriately snap to or lay out correctly with data from Wisconsin or Missouri and vice versa, and so forth. So it's really to provide this larger cohesive system. So we're going to sacrifice some, some precision on the local level to make it work, to make a system broader, to allow interstate communication. Now, I want to say that inconsistency, or I guess the error rating using WGS-84 in local areas is very small. So it's not something we need to worry about necessarily as far as accuracy on location. Google Maps, a lot of our, a lot of industry uses WGS-84 as the coordinate system that they kind of base their data on. So what's the difference between these two things? WGS-84, again, is three-dimensional. State plane systems are two-dimensional. State planes use, so in order to have a two-dimensional coordinate system, we need to have a three-dimensional system behind it that kind of projects onto a two-dimensional surface. So state plane uses this NAD 1983. NAD stands for North American Datum. And then we have our WGS-84. Both of these are considered coincident. They're considered, the same. And to minimize coordinate changes, the NAD 83 is tied to the North American and Pacific plates, whereas the WGS-84 is tied to the International Terrestrial Reference System. So the WGS-84 essentially is based off of an imagined center point in the Earth's center, and then kind of radiating out from there. Whereas NAD 83 is looking at the position of the North American and Pacific plate. to kind of gain that reference of where everything is on a three-dimensional model. So these two coordinate systems were once aligned. However, over time, they've been drifting apart, becoming increasingly different. So that's where converting between a two-dimensional state plane coordinate system into a WGS 84 and vice versa can be a little tricky. There is some error that can occur if we don't use the proper transformation. This is some text from ESRI itself. There are several different types of transformations that we can use to convert from this NAD 83 to WGS 84. They often just label it with a 1, a 2, 3, 4, 5, 6, 7, 8, yada, 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 to differentiate between these transformations. Essentially, with each transformation, it's small mathematical differences in the calculation that you're choosing between. And currently, with what's published on ESRI, suggests that we should use the NAD 83 to WGS 84 5 transformation type. However, that transition number is no longer recognized, or it's deprecated from the ESP or EPSG, which is the essentially a third-party arbiter over accuracy of these different types of transformations to understand which ones are the most accurate. So currently, what one user on the ESRI community suggests is to use this WGS 84 to NAD 83 with this 108190 ID number for the most accurate. However, this is where it gets a little tricky. What I recommend to you is within each state, each state will have their own, local coordinate system that they'll be using. So that transformation may adjust. Which transformation you should use is kind of up for debate, depending on your precise location. And I encourage you to look to state resources for guidance on this particular matter, because whatever transformation you use should be standard across that state, or at least that state plane area. So again, this would be a good idea to understand what coordinate system your CAD system is using and your local data is using, and start that conversation with your state representatives to understand which transformation is most accurate and which one they want you to use. All right, we're near the end, I promise. So now managing multiple schemas, looking at how we're going to handle local CAD and NENA schema types. We have a few options. One is parallel data sets. That's the simplest option. Then we have a master data set option, or an extract, transform, and load option. Parallel data sets are what it sounds like. Essentially, we have our CAD software GIS data, and then our NG9-1-1 GIS data, and they do not mix. They're two siloed data sets. If you need to update or add an address, let's say, then you're going to need to do that process twice. Once for the NG9-1-1 data set and another for the CAD software data set. So it's really easy. You have two data sets. However, you're doing duplicate editing work, which could allow for some error to take place. If you have, you're doubling the workload and needing to manage the requirements of two different schemas. So this is an option. It's the easiest to do technically, but it does introduce some error. A master dataset option is essentially taking both datasets and combining them. So we noticed at the beginning that there is some similarity between my example of CAD software field types and the NENA standard field types. Because of those alignments, we would be able to just, if we have a master data set, we can combine those like fields. And then where there is some discrepancy between the two schemas, then we just separate them out into combine, we'll have all of those fields in one master data set. So we can use attribute rules to kind of automatically populate certain fields based on other fields. It's really easy to export because it's just one data set. There are multiple places for errors. If you enter in an inconsistent field type in one field, it could kind of cascade into others. But the nice thing is that there is just one projection. I say nice thing, but it's complicated. Since we only have one data set, then you're going to have to choose between the coordinate system type. Are you going to maintain all of your data in WGS84 and then transform it into your state plane for your CAD software, or vice versa? Up to you. But that's one disadvantage of the master data set. And lastly, we have this ETL, extract, transform, or load option, which essentially is a scripted program or software that we're able to take your data set and transform it into the schema type, the output that you're needing. So it's essentially kind of a combination of that master data set, but then it outputs a simplified, rigid, I guess, example for NENA standards or for your CAD system software. This is very nice. It allows for less room for error because you have all your data there and it's just transforming it via the script. It is a bit complicated if you're going to build it yourself, or it's going to cost some money if you outsource this ETL. There are several companies out there that provide this service. However, it kind of helps you balance those two competing schema type and coordinate system differences between your CAD software and your NG9-1-1 standard. So looking at this kind of in a matrix here, we have, parallel data sets are very easy to implement. Master data sets are also easy to implement. You're just kind of combining them, while ETLs are a bit more complicated to write out that script and to really think through the exact outputs that you want. Especially if we're looking for anything more complicated than the NENA basic standard. If you're trying to do an ETL that also incorporates the state specific iteration of NENA standards, then it can get even more complicated. Opportunities for errors, we'll just skip over to the far right because I know we're short on time. Opportunities for errors are the highest with parallel data sets because you're having to just do both edits twice. Master data sets a little bit less because you have it all in the same table essentially. And then ETL, it's kind of taken care of in the background. So opportunities for errors are lower.